Hi, my name is Alex Bordei, and in this brief video, I want to elaborate a bit on the concept of rail-type architectures. Right? This is because we've added support for this type of topologies in our 7.4 version of our software, and I find them fascinating, and I think many of you may already know about them, but I still think it's worth talking a bit about for those of you who don't. Right? So, what are rail-type architectures? Right? Where do they come from? Right? So, many of you are familiar with the class topology, spine leaf architecture. Basically, that spine leaf architecture, if you want to use it for very high performance GPU clusters with 32,000 GPUs, where each GPU needs to talk to every other GPU, it ends up costing a fortune, right? You have so many interconnects that would enable many any-to-any communication that it just makes it prohibitive. It is implemented like this in supercomputers, but again, they're very, very expensive. And so for and even for supercomputers, what the folks at MIT and Meta, started thinking, and they wrote a paper on this topic, is how do you reduce the amount of cables and network equipment that you need, but without degrading significantly the performance of the cluster. Right? So they came up with this idea of a rail architecture, and this is actually quite simple. Instead of having that fully connected network, you have a series of spine leaf architecture, still cross topology, but a number of them running in parallel. Right. So, and the way you organize them is essentially by GPU index. So you have the GPU index 1 in server 1 is connected to GPU index 1 in server 2, in server 3, and server 4, and so forth. Right. So in our little diagram here, this GPU here, is part of rail 1, and then together with its neighbor here, GPU 1 in server 2, and so forth. Right. And each of these rails is a fully developed closed topology, spine leaf architecture that scales with the amount of GPUs that you have in each individual rail. Right? Now, what this does, and the MIT paper showed, is that it reduces the amount of cables and network equipment with 77% without a significant degradation in the overall performance. Right? And so this is very, very important. Now, in normal real-life implementations, such as NVIDIA and CP architectures, this is not implemented in this canonical form. Instead, there is, you still have the rails, but there are also super spine switches, right, that interconnect these rails. And the reason for this change in the architecture is not to enable any-to-any communication, even though you do enable that, which simplifies programming overall. But more importantly, it allows multi-tenant environments to function. Right? So in a multi-tenant environment, because that is the vast majority of these clusters are installed for either cloud providers or enterprises that want to have multi-tenancy, what you need is to be able to allocate GPUs and partition them, for respective tenants. Right? So you want this GPU 1, GPU 2, and GPU 2 from here, and maybe 3 to be part of the same tenancy, right? But without sacrificing the performance and the rail, architecture that would reduce the number of cables and maintain the performance overall, right? So, so that's why you have the spines, and you also have the capability by using software like MetalSoft to create those, those tenants, those partitions, right, within the respective rails or across rails, if need be, to interconnect the GPUs that make up a particular tenancy. Right. So MetalSoft builds the underlay as well as the overlay by partitioning the network to enable this type of multi-tenant rail-type architecture. Thank you for watching.